Welcome to Unit 2. In Unit 2, we're going to be studying forces. Now, in Unit 1, we looked at kinematics, which we did all of our formulas that have to do with motion. Now, in Unit 2, what we're doing is what's called dynamics. So, dynamics is why things move, and they move due to forces. So, in this unit, what we're going to study later on is a concept called inertia. And inertia states that things that are in motion stay in motion. Things that are at rest want to stay at rest, and the only way we can get things to move or stop moving is to exert a force on it. What we're going to be looking at in U2A1 is forces and free body diagrams. A force is just a push or pull, and what we're going to see later on in this unit is mathematically force is equal to mass times acceleration. The greater the force, the greater the acceleration. If we have a larger mass, it is harder to accelerate that larger mass. And we're going to measure this in a unit called newtons. Now, some of these forces are easy to understand. So, for example, an applied force would be like when we push a lawnmower or pull a toboggan. So the best way I can talk about what an applied force is just by using examples. It's when we actually push or pull something. Now, another one that's easy to understand is the force of gravity. Well, you might think gravity's easy to understand because we know what would happen if you fall off of a ladder. But to be honest, Newtonian physics, and which is what we're doing, is only explaining mathematical relationships. So anything that has a large mass has a significant force of gravity. For example, the planet Earth. The moon has 1/6 the gravitational pull that Earth does because it has a much lower mass involved with it. The force of gravity on Earth has a constant of 9.8 meters per second squared. Now, what that means is for every second we fall, we increase in a speed by 9.8 meters per second. The reason there's a negative sign is that negative sign is direction, and that's like saying we fall down. Okay, that's where that negative comes from. Now, what we don't describe here is why gravity occurs. We only say things like the larger the mass, the greater the gravitational pull. Another thing we can say is the further you get away from Earth, the less that gravitational pull. But we have to get quite a ways away from Earth before we have a significant effect on that 9.8 meters per second squared. And that has to do with the radius of the Earth being quite large. But what Einsteinian physics does is it tries to describe why gravity occurs. And that's something called a space-time continuum. Now, Einstein used this to discover black holes. All you have to know is that gravity occurs, it is a force, and it can pull us down towards the Earth. One that's harder to understand is a normal force. So I need you to try and wrap your head around this to understand what a normal force is, because we're going to be using this quite a bit in this unit. If we have a brick, and that brick weighs 1 kilogram, it's being pulled down by a force of gravity onto that tabletop. Force of gravity equals that 1 kilogram, or that mass, times that acceleration of 9.8 meters per second squared equals 9.8 newtons. A normal force is an equal and opposite force. So what we're going to find out in this unit is that forces work in pairs. For every force, there is an opposing force to it. So the normal force would be 9.8 newtons in the opposite direction. Now, to give you a practical idea of what a normal force is, gently put your fingertips on the top of a table surface. You can feel that table pushing back onto your fingertips. That's a normal force. Push even harder with your fingertips and it feels like the table's pushing even harder up into you. That is a normal force. Anytime something is in touch with the surface, there is a normal force. Now, this doesn't have to be on the horizontal. This can also be on the vertical, and that normal force would push out. The next one we're going to do is a force of friction. If we have an applied force, what's going to happen is the faster we push, we're going to have that or if we push this and start moving it, we are going to have a force of friction moving in that opposite direction. We're not going to say too much about that, but put your hand on the top of your book now and push your hand along. You'll feel friction holding it back. Now we said it's any push or pull is a force. Imagine this. If we take a puck and put it on the ice and we push it, physics states that because of inertia, that puck should keep going forever. There must be a force that stops that puck from traveling, and that force is going to be the force of friction. It's eventually going to slow that puck down and stop it. Tension force is when something is attached to a rope. So if we have a block on a ramp, that force of tension is holding that in place. Now, tension becomes very important when we do problems involving things like elevators. Listen, this is just an introduction to these forces. Make sure you're going over the course content. Make sure you're watching some video in places like the Physics Classroom or Khan Academy. What I'm going to do now is go over some free body diagrams. So in this first lesson, U2A1 in physics, I said one thing that you have to do is understand these different types of forces we're going to take a look at. Now what we're going to do is free body diagrams. So the first one says we have a block on a table. So what you do is you make a simple drawing. Now it says that block is being pushed. Let's look at all the forces that might be on that block. If we're pushing it to the east, there's an applied force. There's different ways of drawing these diagrams. I usually draw it by taking the direction the arrow's going in, putting it outside of the object. Some people draw from the middle of the object. There's a force of gravity pulling that block down. If there is a force of gravity, there's an equal and opposite normal force working in this direction. And if we push that along, there's going to be a force of friction acting opposite to the applied force. Okay, a book being pushed against the wall. There's going to be a force of gravity acting on that book. There's going to be an applied force pushing the book against the wall. Now we said a normal force acts opposite to any surface, so we are going to have a normal force there. Here's a really interesting one. A baseball being hit. If you have a baseball bat and you hit the baseball and the baseball starts flying through the air, there's going to be a force of gravity pulling that down. Now here's the interesting point. The applied force is only when the ball is in contact with the bat. Once it leaves the bat, there's no force on it anymore. There's only the force of gravity. Now, you could say there's a force of friction due to air resistance in this direction. Now, remember, applied forces are only when things are in contact, not when they're flowing or going through flight in the air. A block is sliding down the ramp. What is causing the block to slide down the ramp? Well, there is a force of gravity pulling it down the ramp. So the normal force is always perpendicular to the surface, so the normal force would look like this. Is there an applied force in here? No, because the reason that this block is sliding down is due to gravitational pull, pulling it down the ramp on an angle. What about friction? Friction is always opposite in direction to the movement of the block. So if the block is moving down the ramp, there is the force of friction. These are different free body diagrams. This is a big part of this unit. There are more examples in the content. Try to go over this video a couple of times to pick up some of these points. I tried to give you varied examples to do some of these free body diagrams.